Good morning, everyone. This is Andrea Ferretti from the Nanoscience Institute of Italian CNR, Modena, Italy. And today I'm giving a theoretical overview of what the photoemission experiment is, how it connects to quasiparticles and lifetimes, and in general, how it can be explained by using the Green's function theoretical framework. So here is the outline of my talk. I'll first spend a few words about the ARPES experiment itself, and then I'll make a connection to the Green's function theory, and then I'll describe the GW approximation to the self-energy as one of the key approximation of the key ingredients that enters the theory. So let's start from the ARPES, and at variance with adsorption, where we basically have a neutral excitation of the system, meaning that the system stays neutral upon excitation. In direct and inverse photoemission, the number of electrons in the system changes. And in particular, in direct photoemission, we have the system is hit by an incident photon and an electron is emitted, and vice versa for in inverse photoemission. Here is an outline of a sketch of a description of the photoemission experiment setup. What is important to note here that there are a number of parameters that can be controlled in this experiment, and notably one is the frequency of the incident photon, but also the angle at which the electrons are ejected from the system, and or the spin. In particular, this control of the angle that gives rise to the name of angle result photoemission allows the user basically to address the K-point dependence of the electronic structure. So it's the experimental way we have to measure electronic bands as we are used to think about. In practice, what happens is that if we look at a non-interacting simple model, here we have the density of states of a system, and we absorb a photon, and then the features in the density of states are mirrored somehow in the photoemission signal. And what is measured in the photoemission experiment is actually the kinetic energy of the outgoing electrons. And this basically allows us to identify the binding energy of the electrons within the material. Of course, in direct photoemission, this is true just for occupied states, since we are extracting one electron. And here instead on the right, I'm just plotting some state-of-the-art picture coming from our labs. These are data obtained at the synchrotron for a system that is made of graphene adsorbed on a transition metal, either cobalt or nickel, and we can nicely follow the band structure of the system. Okay, coming to a theoretical description of the problem. Basically, we can use Fermi golden rule, and so we have an initial state, and then we have a final state. The perturbation is given by the photon, and we have just to specialize the final state to the experiment we want to describe. That is, we have an electron that is ejected from the system, and n-1 are left into the problem and into the system. And something that can help to rationalize this process is this cartoon that is the basis of the so-called three-step model, where first the an electron is excited, and then the electron travels through the system, and then eventually is ejected. It has to go through the surface and get into vacuum. By keeping this in mind, basically one could construct the final state that is quite complicated in general if one wants to describe the whole process by a single state. Instead, by making the so-called sudden approximation, where we assume the electron, the outgoing electron, to be fast enough, we can approximate the final state in this form. It is the product of an excited state with n-1 electrons plus a plane wave in vacuum. And by this approximation, we can basically rewrite the photocurrent in this form, where this quantity highlighted in orange is the so-called spectral function that, as I'll discuss later, can be written in this form. So it's basically a matrix element of involving excitations at n-1 electrons. Okay, so this is what we would need to describe the photoemission experiment. Let's now look at what are the mathematical objects that we can use to do this. And this mathematical object is actually the interacting many-body Green's function. Here is the definition taken from textbooks. And if we look at it in closer details, this was already discussed yesterday by Pedro Melo. We see that basically here we are accounting for an electron that is added at T2 x2 and then destroyed at T1 x1, or vice versa for the holes added at T1 x1 and then destroyed later on. In between T1 and T2, basically, or T2 and T1, we have a dynamics with an extra electron or an extra hole. And so that's why, in order to expand these dynamics, we need to address or excited states that are charged. So this object basically embodies the knowledge about charge, excited states, charge, excitations. Here is a form that is called Lehmann representation, an exact representation, exact form we can give to the interacting Green's function. That is quite nice since it really resembles what we have for non-interacting systems, where this Fs would be the non-interacting single particle orbitals and epsilon s would be the eigenvalues of our non-interacting Hamiltonian. Instead here, epsilon s are total energy differences of many-body total energies at n excited n-1 or n+1 electrons, and the orbitals become these Dyson orbitals or Dyson amplitudes that are defined with this matrix element involving, again, the many-body ground state at n particle with excitation at n-1 or n+1. Importantly, these Fs are not orthogonal, they are not normalized, and also they are many more than, actually infinitely many, than the simple non-interacting case. In those cases, you have for each electron, you have one orbital. Say here we have many more. So if we go back to our problem of giving a theoretical description of photoemission, we were writing the photocurrent in this form involving the spectral function. And indeed, the spectral function exactly involves the Dyson orbitals. And indeed, the spectral function can be written as the imaginary part operatorially of the Green's function, or can be used by Kramer's Koenig or Hilbert transform to write the Green's function. And it has this expression here in terms of the Dyson orbitals. And if we take just the diagonal part of it, we obtain this object that is the local spectral density, that is nothing else than the local density of states properly defined for a many-body system. Okay, as we also know from textbooks, the Green's function obeys the Dyson equation that is written in the first line. It is basically a connection between the interacting Green's function and the self-energy. Basically, if we know the self-energy, we know the interacting Green's function and vice versa. That is formally solved with this inverse. And if we put the two together, that is possible when we work with discrete states. So if we put the formal solution with the inverse involving the self-energy and the Lehmann representation that we have just seen, possible when we have discrete states, we obtain this equation. Is quite famous, where we see that the self-energy basically plays the role of an effective potential that is orbital dependent. Also, we know that the self-energy is also non-local and non-Hermitian. And this basically happens for orbital by orbital. Okay, alternatively, one could just take the formal solution of the self-energy and consider the frequency as an external parameter, diagonalize the equation with this frequency parameter and obtain this other expression for the Green's function, where the frequency is now a parameter for the left and right eigenvectors, as well as for the energies. And since the self-energy is in general on Hermitian, we see that the eigenvalues ES are also complex. So the poles of this Green's function can actually become complex. And we could refer to this expression, to this representation as a quasiparticle representation. The two are actually both exact, and but lead to two different physical pictures. The Lehmann representation basically leads to a picture where you have infinitely many poles given by epsilon s. Epsilon s is a total energy difference, so those are poles on the real axis. And in the continuum limit, these form a branch cut, a mathematical branch cut on the real axis for the fully interacting Green's function. And instead, the quasiparticle representation basically looks at this structure in the, if you want, in the spectral function of the problem as originating from fewer poles that are far apart from the real axis. So with a single object, a single pole, basically we define a multitude of structures that is also useful physically, since being these poles far from the real axis, they gather an imaginary part that results in a broadening of the structure. The two expressions are exact, and the mathematics is quite subtle here, since basically we have two analytical continuations of the same object, and this requires, for instance, to have these belonging to different branches in a multi-value function of the complex frequency. For mathematical details, I'll refer you to, for instance, the works by Farid or to the Onida Irene Rubio Review of Modern Physics 2002. Okay, here is the general picture that arises when including excited interactions in the description of the system. So here is this H naught Hamiltonian that is a Hamiltonian for an interacting system, and then we take a self-energy that we assume diagonal for the sake of simplicity on the eigenvectors of the non-interacting Hamiltonian. And then if we do a Taylor expansion of this frequency dependency of the self-energy around this EI energy, that is the non-interacting energy plus the real part of the self-energy, basically we can rewrite the resulting Green's function in this form here at the bottom left as the Zi renormalization factor over a pole with a renormalized position of the on the real axis, but also an imaginary, a finite imaginary part. This Zi is called renormalization factor and depends on the derivative, frequency derivative of the self-energy, and the imaginary part of the pole is actually related to the imaginary part of the self-energy at that energy. If we look at the spectral, the rising spectral feature, we see that infinitely sharp Dirac delta, that is the contribution to the density of states of a non-interacting Hamiltonian, actually becomes is shifted, is broadened because of the imaginary part. And also we see that some spectral wave is cast away into satellite features, meaning that the weight of the main peak is also renormalized, so it becomes smaller than 1, typically. So as a summary, these are on the left and the right, the differences between a non-interacting K-resolved density of states and an interacting spectral density. That is that we have a renormalization of the features, we have satellites, we have lifetimes in terms of broadening and energy shift as renormalization. And all these features are actually can be captured by the dynamical and non-Hermitian nature of the self-energy, and actually can be described by, these features of the self-energy. So physics is actually cast into these extra complexities that are required for a proper self-energy. Okay, this pertains to the general theory of the Green's function. Now, to make the theory practical, we need to make approximations for the self-energy, and the most common and most used in this theoretical framework is the so-called GW approximation. This was introduced by Lars Hedin in 1965. Main idea is that Hedin introduced an extra perturbation term in the Hamiltonian that eventually is taken to zero at the end of the calculus, but allows us to take response functions. And so that leads to the introduction of the screening as a key concept in the theory. Hedin was able to reformulate the problem exactly by means of 5 equations, 5 Hedin equations. You can recognize the first one is the Dyson equation that we have just seen. And this comes from with another equation for sigma that expresses sigma via an integral with 2 objects, W, a screened interaction, and gamma, the vertex. W is another Dyson equation involving the polarizability. The polarizability is also written in terms of the Green's function and the vertex. And finally, basically, the vertex itself is probably the most complex object in these equations as a kernel. So it obeys another Dyson-like equation. This, you see that there's gamma both at the left and at the right. And the kernel of this equation is this d sigma in the G. It is an effective 4-point renormalized Coulomb interaction. And by the knowledge of this vertex, basically we can compute all the other quantities, and these are a set of complete equations, though it's very complicated one, and one needs approximations. Just as a side note, basically all these Dyson-like equations can be seen as a geometric series with a formal solution of this form. Actually, resummation is not always possible because of the known limitations in the domain of convergence, but just for the sake of describing what we are obtaining, we can think of W or the Green's function coming from multiple and more complex steps add one on top of the other. There's also a graphical representation by means of Feynman diagrams that it is particularly useful since so these equations are complex, and what is actually relevant is the connection between the objects I just described. So the fact that, for instance, the self-energy is a connection between G, W with the vertex on one side, just to name one. And if we want to make these equations treatable, we need, as I mentioned, to add approximations. And the easiest approximation is just to consider a point vertex, that is to drop this blue highlighted extra term in the Dyson equation for gamma. That makes gamma point, and so we end up with the polarizability being the product of GG and the self-energy being the product of G times W. That is this expression here, and this is the so-called GW approximation. Here we see that the polarizability is the product, this the irreducible polarizability is the product of two Green's function, that is basically polarizability treated at the independent particle level. We can write diagrams for GW. Very simple one is this, where we have G times W, but we can expand W in this series due to the Dyson equation when we see appearing RPA bubbles, the first term being the R3-Fock one. And it's important to note that since we have made approximations, these are not all the diagrams that could be required to having the exact self-energy, but are just a subset. A first diagram that is missing is already the second order, and it is a second order exchange diagram that is actually not in the GW self-energy. And this would have an impact on, for instance, self-interaction issues that I'm going to discuss by the end of this presentation. So how does it work? Well, it works very well. The GW has been used extensively since the 80s numerically and applied to a number of systems. And for instance, when applied on top of Kohn-Sham DFT in a non-self-consistent way, or in this case, even in this work by Mark von Schiffgar, even in a self-consistent way, it gives a very nice renormalization of the fundamental gap of semiconductors, and was also applied to molecules to estimate the ionization potential. And so results are significantly improved with respect to approximate Kohn-Sham treatments. Still, there are a number of open issues. First, as I just mentioned, GW is a non-self-interaction free theory. So if we apply GW to one electron systems, we do not obtain the exact result. And this comes because of the RPA polarizability that is non-self-interaction free, and that basically introduces some self-screening effect into GW, and this was long known in the literature. Second thing is GW comes from an approximation to the Hedin's equations where vertex are neglected, and so corrections beyond GW basically include vertex in the treatment. This is a very complex and still very lively field of discussion in the developments in the literature. Also, for simple systems such as the homogeneous electron gas, it was shown that self-consistent, so the GW basically does not describe very well satellites, and even worse when going with to full self-consistency of the method. Satellites are really damped. This was also recently reported for more realistic systems. And still concerning satellites, the GW has been mixed with combined with the cumulant approaches such as done here, and that has been shown by several groups to improve significantly on the position and intensity of the satellites, though as clearly discussed in this paper here, in order then to estimate the photoemission signal, you actually need to include also description of the extrinsic losses that are not described at this level of the theory. And let me conclude with this work, a very recent nice paper about the simulation of photocurrent, where state-of-the-art results taken at the synchrotron for aluminum are compared with GW plus cumulant for what concerns some of the intrinsic aspects. But if you really want to simulate the experimental photocurrent, you really need to also add some extra effects related to electron phonon coupling and temperature that can still be considered as intrinsic, but also some extrinsic losses proper of the experimental setup. And if you do that, you reach very interesting and nice agreement with the experiment. And with this, let me thank you for your attention. I'm open for questions.